Okay, so we've talked about addition, subtraction, and scalar multiplication. What happens if we try to multiply two vectors? What does that even mean? You know, 6 steps this way and 4 steps this way. How do I even, what does that even mean? Okay, so let's imagine two vectors again. Some vector A, let's say it's 1 unit plus 5 units, and vector B, let's say it's 4 units plus 2 units. And just for clarity's sake, we can draw those two things. It's all in quadrant 1. Four, 2, and 1, 5. So that's vector A, and that's vector B. How do we multiply directed quantities? And to answer that question, there are actually a couple different ways to answer that question, but one of them, I'm going to ask you to think back to multiplying signed integers on the number line. Right? Or old school multiplication. Suppose we wanted to multiply 2 and negative 3. And the answer we know is negative 6. If we wanted to multiply 2 times 3, the answer would be 6. And now let's unpack what that means a little bit. 2 is a number that points to the right on this number line. Negative 3 is a number that points to the left. Positive 3 is a number that points to the right. And just for sanity's sake, both of those numbers point to the left. The product is just 6. One way to keep track of what happens when we're multiplying positive and negative numbers is maybe a mnemonic that we learned back in grade school. You know, when bad things happen to bad people, that's positive. That's good because they were bad. They deserved it. When good things happen to bad people, well, that's bad because they didn't deserve it. And so on. Another way to think about how this product thing works, the answer is 6. 2 times 3 is 6. 2 groups of 3 adds up to 6. Are we talking about things in the same direction on the number line or opposite directions on the number line? Anytime the two numbers are in the same direction on the number line, the answer is positive. Anytime the two numbers are in opposite directions on the number line, the answer is negative. So negative multiplication, as far as number lines go, was always the product of directed quantities. 2 is directed to the right, negative 3 is directed to the left, and we were happy to multiply them and get negative 6. We know how this is supposed to go. We just need to figure out how to get it so that A and B are on, or at least partially, on the same number line. Because once they are, we know how to multiply them. Okay. Vector B, let's say, is directed along this number line, right? That address there is, I don't know, it's like 3 units along the B line from the origin that way in the direction of number line for direction B. We could think about any old vector that we write in terms of 2 perpendicular components. We've got x and then y. What if we called them x and perpendicular to x instead of saying y? What if we called them b and perpendicular to b? We could, if we wanted to, we could write vector A as a piece along the direction of B. I'm going to say A sub B. You know what? I'm just going to say A parallel in the B direction. And a piece that's perpendicular to B in the perpendicular to B direction. Weird looking unit vectors, but you get the idea. There's a piece along vector B, this one, and a piece perpendicular to B, that one. And we could express vector A as first to do this, and then from there do that. And that gets us to address A just as well as following A's directions, straight up. So this I'm calling A parallel and A perpendicular. Okay, fine. Actually, I'm going to move that label because how do I figure out what A perpendicular or A parallel are? And the answer is that I need to talk about this angle, the angle between A and B. If we know the angle between A and B, then we can express A parallel in terms of this right triangle that we're making here with the actual hypotenuse as vector A itself. So A parallel we can get from cosine. A parallel is a directed quantity along the number line of B. We know how to multiply those. We can just multiply. We want it to be so that if A and B are more opposite directed than they are parallel directed, that the answer is negative. And the cosine is ready to do that job for us. If we let the angle phi grow to more than 90, cosine of 120 is negative. Cosine of any angle greater than 90 and less than 180 is negative. So the cosine phi is going to get us the positive or negative. It's going to get us the parallel or anti-parallel kind of nature like we had here. These two are parallel, so their product was positive. These two are anti-parallel, so their product is negative. These two, on average, kind of generally, both point that way. They're more positive, more parallel than they are anti-parallel. Both vector B and the component of A along B point in the same direction. Let's define this kind of product as the scalar product, because what we're ending up with is not a vector. A is a magnitude, B is a magnitude, and cosine is just a number. So this is a scalar answer we get when we multiplied two vectors, and the answer is essentially, how parallel are they? What is their product, and how parallel are they? Which is always what we were asking, really. Did we have to use B? What if we used A? A's number line is along that direction, and vector B has a component parallel and a component perpendicular to that direction. That parallel component is vector B times, oops, I'm sorry. So that felt weird. Is magnitude of B times, again, the cosine of the angle phi between the two of them. So we're going to end up with A times B parallel to it, which is, again, A times B cosine phi. So it's going to get us the same answer either way we think about it. Okay. This is true. This is a definition that we will run with. That A dot B is how we can read that aloud. The scalar product is equal to the product of their individual magnitudes, A times B times the cosine of the angle between them. Not the angle necessarily of either one, but the angle between them. This allows us to, make some nutshells. I hat dot I hat. Suppose we wanted to dot 1 I hat dot 1 I hat. What is the product of two unit vectors in the x direction? Well, it's the magnitude of the first part of the product, the first factor, which is 1, times the magnitude of the second part of the multiplication, which is also 1, times the cosine of the angle between the x-axis and the x-axis, which is 0. The cosine of 0 is 1, so this answer is 1. What about I dot j? Again, 1I dot 1j. The individual magnitudes of the two pieces are still 1, but the angle between I and j, that's between x and y, is 90 degrees. The cosine of 90 is 0, and that's 0. And I think you can see where we're going. The dot product of a unit vector with itself is 1. The dot product of a unit vector with any other unit vector is 0. Any vector other than itself is 0. So that allows us to write the scalar multiplication of A and B two different ways. This way, and component-wise. Let's see what we're doing here. A dot B equals, apparently, just kind of like we did for addition. We write it 1i plus 5j dot 4i plus 2j. If this goes like any other thing we've ever seen, we can distribute. Distribute across the dot into the other one. That's 1i dot 4j, like foiling, right? 1i dot 2j. Plus 5j dot 4i plus 5j dot 2j. Now, I dot j, that's 0. The angle between them is 90 degrees. So even though the product is 2, we still get the cosine of 90. That term disappears. This term disappears. They both go to 0 because we're doing the dot product of perpendicular components. The only terms that survive are the, oops, I'm sorry, this is 4i, are the terms that dot the same unit vector together. And we take the magnitude of one, the magnitude of the other, 1, 4, and the cosine of 0, because I dot I gets us 4. This gets us 10. And the answer is 14. 14 square units. It's not a vector. It has no direction. How parallel are they? And what is the product? This kind of thing, the fact that these two terms disappeared and we just have the terms that multiply like components, means that we have another formula for the dot product. All we need to do is multiply the components, not the vector components, just the scalar components in each direction, add the results, and we're done. Cool.